Hi, everyone. Today we're going to continue looking at states of matter. And to start with, I'm very interested in you learning really about how the particles in matter behave when they're in those different states. As always, if you need to get a hold of me, please use my email address. That's rcrawford@jcpsmail.org. Without any further ado, let's jump right in. All right, so when we talk about the states of matter, I would be remiss if I didn't at least take a moment to review what matter is. The most basic definition that you'll see in science classes for matter is anything that has mass and volume. Now, when we talk about mass is really just how much stuff is inside of an object. So, really, the way I really appreciate students thinking about this is things that are less massive have fewer particles inside of them, whereas things that are more massive, they're made from more particles. And by particles, we really mean atoms and molecules. Okay, so mass is just a measure of the amount of matter in an object. When we talk about volume, we're talking about the amount of space that an object takes up. So, if we say something takes up a lot of space, well, then we can say something that takes up less space. And so volume is the amount of space an object takes up, whereas mass is the amount of matter in an object. Okay, so that's the most basic definition you're always going to run into, but I don't feel like it's the best one. This is really the definition that I think is most helpful for you. When you think of matter, I just want you to think about anything that's made of atoms and or molecules. That is mostly everything on Earth, excluding energy. And so that includes anything that's land, water, air, living things, pretty much anything you can imagine that is made of atoms. And that is, of course, that generic term that we call matter. So, what are states? Because we're talking about the states of matter. Well, we really just mean those different physical forms of matter. And of course, I mean solid, liquid, gas. One of the substances here on Earth that we encounter in all three states of matter pretty commonly is, of course, water. So in its solid form, solid physical form, we call it ice. Now in its liquid form, which is where we most often see it when it's outside of temperature extremes, we just call it water. We don't say it's liquid water. When it changes into a gas, we call it water vapor. So those states are just these three physical forms. So states of matter. So let's take a look at those particles. The very first thing I would want you to understand is that you need to commit to memory how the particles move. Because how the particles move and what they're doing when they're moving, and they're never still, is really sort of a key to success. So the particles in solids, we're going to find that these particles inside of a solid, here inside of this tube, this Erlenmeyer flask, we're going to find that they are vibrating in place. These atoms in here are not able to move around from position to position. Okay, so they can only vibrate or jiggle in place. If we were to compare that to what's going on with the particles of a liquid, how are they moving? Well, these particles are able to sort of rotate around one another. They're able to slide past each other and tumble over one another. So the particles themselves are able to move from place to place. If we look and compare how a liquid is to a gas, we're going to find that gas particles, well, they are moving very fast. These particles can move at over 1,500 miles per hour, and they just bounce around at really high speeds. And so vibrate in place is what solids do, rotate around, slide past, and tumble over each other. That's what we're going to find for liquids. And these gas particles, well, these things are just bouncing around at very high speeds. All right. In addition to what is happening with the particle motion, we need to think about how close together the particles are. This is something that the reading brought up, and I think some of you maybe took some understandings from the reading that aren't true. So these particles inside of a solid, they're very close together. They're often organized in rows, and we're going to find that sometimes these can be closest together. Now, that is not always true. I do want you to know that if we look at liquids, the particles are also very close together here. Sometimes in solids, we're going to find that they are closer together, but it's not always the truth. So in general, the particles in both solids and liquids, we're just going to say they're very close together. Whereas if we compare that to the particles in gas, we're going to find that these particles in gases are very far apart. So we have some similarity here between the solid and liquid, but not so much with the gas. Okay, Um, One of the things, some of you understand that to move between these phases of matter, that we can add heat or remove heat. And so we want to also look at the amount of heat energy that each one of these states of matter has. So if we look at solids, they are the least jiggly. They have the least motion. Remember, they can only vibrate in place. So we would say that they don't have very much motion and not very much heat. As we move up that continuum, we're going to find that the particles in a liquid, well, they have more heat energy. Now, they don't have the most, but they have some heat energy. And the particles in a liquid, if we were to move some of that heat energy from them, we would take away some of that particle motion and could change back into a solid. Let's go ahead and add some more heat energy, because when we look at gases, we find that gases have the most energy and they also have the most particle motion. And so least, least energy and particle motion, we find that in solids. The most energy and particle motion, we find that in gases, and liquids are somewhere in between. Now, I just want to do a quick, have you remember that we talked about something called IMF, intermolecular forces. So intermolecular forces are those attractive forces between different molecules or atoms. And so, like these two water molecules that are shown here have an attraction to each other. Now, we don't want to confuse these with intramolecular forces. These are the forces inside of an atom, and of course, by that we mean chemical bonds. We're just talking about the forces when we talk about IMF that are between different molecules or between different atoms. And try to keep in mind that when those particles are very close together, then we have a very strong IMF. And as those particles get further apart, we find that the intermolecular force, that attraction, gets weaker, and we can eventually get particles so far apart, molecules so far apart, that there is actually no intermolecular force between the particles. Now, so let's look at attraction in each one of these states of matter. So when we have solids, of course, we said that the particles in solids are often very close together. We're going to find that these particles in solids, these atoms or molecules, have a very strong attraction to each other. That IMF is very strong. Now, as we sort of once again move along, when we look at liquids, well, this very strong attraction, we've maybe added some heat to change the solid to a liquid. This very strong attraction has been weakened. When we move over to a gas, we can see that these particles are very far apart. And remember, the further apart particles are, the less likely we are to have any attraction at all. And in gas particles, there's no real attraction at all. So remember, adding heat is going to create more motion, which is going to push them further apart, and it's going to weaken forces. How free are the particles to move? So when we're talking about free to move, we also have to think about really what's going on with the attraction between the particles, because these attractions between particles are what limit the freedom or give the freedom. So when we look at solids, these particles are not free to move at all. They are locked into place. There is very strong intermolecular forces there. That attraction is very strong, so they stay put. They can still jiggle, but they stay locked into a position. They can't move from place to place. When we look at liquids, on the other hand, we have given it more energy. We've given a liquid more energy, which has given these particles more motion, and as a result, they get pushed a little further apart. And so, with liquids, we find that the particles in liquids, they're able to move around. They have more freedom. Notice, though, that they still stay clumped together, right? So they still have some attraction, but they are not locked into a position. They can still move around each other, slide past each other, rotate around. When we look at gases, these particles in gases have a lot of energy. As a result, they have been pushed very far apart, and these particles are completely free. They are able to bounce around at very high speeds, and you have complete freedom with gas particles. Really, the IMF is completely gone. So that really covers it for our states of matter, particle behavior. We will talk a little bit more about how the behavior of these particles affects the actual properties of solids, liquids, and gases in the next video. Hope you guys have a great day.